Hello and welcome to a lecture on mechanics. In this lecture we will learn about some important rules for drawing shear force and bending moment diagrams, and these are generally, most of them are based on the basic properties of the derivatives that you presumably reviewed just before watching this lecture. And I will start with the first rule, which is a general rule, it's not based on the derivatives, which says that the bending moment is zero at the ends of the beam, or as long as the beam is either free or supported by a pin or a roller, or anything that allows rotation at the ends of the beam. If the beam ends or either end is fixed, or if there's an external moment applied to that end, then that moment there will not be zero anymore. Also, if you have a hinged beam, the moment will be zero at the location of that hinge, because the hinge allows rotation freely, so the moment must be zero. Now, with regard to the shape of the distributed load, if that is uniform, then the shear force will be linear and the bending moment will be quadratic between those points between which the load acts. So you always have to indicate the shape of the diagram if it's anything else than linear. So if it's quadratic, you have to write on it quadratic, so we know the shape of the diagram. Now, if the distributed load is linearly distributed between 2 points along the beam, then the shear force will be quadratic and the bending moment will be cubic between those two forces. So in this case, you'd have to indicate that the shear force is quadratic, and you'd have to indicate that the bending moment is cubic. Now, also based on the properties of the derivatives, the change in shear force between these two points along a beam equals to the negative area under the distributed load acting on the beam. That's very important because you can easily determine, you can calculate the value of the shear force. But the key word here is the change, not the total magnitude of the shear force, but the change of the magnitude from one point to another point along the beam. Also, in order to determine how the shear force diagram looks like, the slope of the shear force diagram will equal to the negative of this distributed load that acts on the beam. So if the distributed load is positive on top of the beam, pushing the beam downwards, then the shear force, the slope of the shear force will be negative. So the shear force will move downwards. The slope will be negative. So rules 4 and 5 are very important rules that will help us determine the magnitude and the shape of the shear force diagram. Now, rules number 6 and 7 are similar to rules number 4 and 5, but now these apply to the bending moment diagram. And again, rule number 6 involves the change in bending moment. So that change between 2 points along a beam equals to the area under the shear force diagram. So look how simple things become now, because if you have drawn already the shear force diagram, you can calculate the area under the diagram and then very easily determine the change. And again, the key word is change in the bending moment between those 2 points. So the change, not the actual value, the change. And then obviously you would need to figure out how the bending moment diagram would look like. And rule number 7 is very helpful to us in determining the slope of the bending moment diagram, which equals to the value of the shear force. Now, also from the rules of the derivatives, wherever the shear force is zero, intersect the zero axis, then bending moment will be either a maximum or a minimum. Of course, it will be a local maximum or a minimum, but somewhere along the beam you will have a real maximum value, either positive or negative, and that you will see later on is very important for designing the beam against failing in flexure. Now, what happens when we have disturbances, when we have these concentrated point forces or moments? Well, with regard to the former, concentrated point forces will produce disturbances in the internal forces diagram as we saw earlier. The shear force will, so to speak, jump with an amount equal to the magnitude of that concentrated force, and the bending moments will have a kink, and the kink results from the sudden change in magnitude of the shear force, which is an indication of the slope of the bending moment diagram. So the slope of the bending moment diagram will change suddenly because of the sudden change in the magnitude of the shear force. Now, along the same line, if a beam has concentrated moments acting on it at some points, then these moments will have no influence whatsoever on the shear force diagrams. So you can ignore these moments totally when you draw the shear force diagrams. But in the bending moment diagrams, they will produce similar disturbances in the forms of, so to speak, jumps in the bending moment diagram. So there will be a sudden change in the magnitude of the bending moment when you go from the left-hand side to the right-hand side of the point where a concentrated moment is applied, and the magnitude of this jump equals exactly to the magnitude of the concentrated moment that's applied at that point. So these are the 10 golden rules explained very briefly. So please try to understand these rules and use them, keep them with you when you solve problems, and use them as much as you can, because if you know these rules, you will have virtually no problem, no difficulty when drawing shear force and bending moment diagrams. They will become very straightforward to do. So thank you very much for watching this lecture, and in the next few lectures we will do some examples in order to understand how to draw these diagrams correctly and how to apply the 10 golden rules for that purpose. See you at the next lecture.